So welcome everyone to this week's Origins Colloquium. It's a pleasure to be hosting Matthew Hayes here in Gothenburg. Matthew received his PhD from Stockholm University in, we said,
2007.
2007. He was then a postdoc in Geneva and also in Toulouse before returning to Sweden, to Stockholm, on a series of projects before being hired on his faculty there, where he's now a professor. And Matt, I've known for a number of years now as one of our key collaborators to study the high-redshift universe. So it's great to be able to hear his thoughts and opinions, and we'll have a discussion about what's really going on at Cosmic Dawn. So welcome, Matt.
All right, thanks very much, Jonathan. I guess everybody here hears me okay, and I assume online as well. So this is going to be a very, very general talk about, just some of the updates from the first sort of billion years or so of our universe, primarily based upon JWST and Hubble observations that we've been involved in some way in Stockholm. Of course, there's tons and tons of other results coming out there from all around the world. And I have many themes that I want to touch upon. Some of them are these galaxy and AGN surveys we've been talking about over the last day or so. I want to talk a little bit about chemical enrichment as well. And then I have some parts about the ionizing radiation produced by the first galaxies and what that means for the state of the intergalactic medium at redshifts beyond 6 or so that I hope to come on to, although I am cognizant of the fact I have half an hour and maybe I'm not going to get to
we can discuss.
But exactly. So, I mean, if you want to talk about any of these other things sort of outside of this room or later on, then please feel free to do that. Of course, this is not work that's been happening in a vacuum. I have to thank a large number of people on various different projects for their inputs and support and all of the work that they have done. And it doesn't change slides. Now it changes slides. So this is my introductory slide to all of galaxy formation, because one thing that I don't do is theory. But I have read Rachel Somerville and Romil Davir's annual review paper on just how to build galaxies inside of computers. And what you typically do is start from very high redshift somewhere before the galaxies have really formed and run your simulation down to whatever lower limit you think you can get away with, incorporating all of this physics that's sort of listed here inside of a cosmological framework. Gravity we think we understand pretty well, and then there's all the hydrodynamics that gets very complicated. Things like stars and black holes make things even more complicated. And then when you have the feedback processes that come from this and reionization, it all sets up a really complicated, very long time duration, very different scale, lots of nonlinear physics, makes for stuff that we really can't solve. So we put everything inside of a computer like this, and it's really, to me, I really think it's really an amazing fact that we can come up with this sort of simulation data that you see here, and you can give mock light cones from the simulations to observers, and they really couldn't tell you often whether you were looking at a simulation or an observation. And of course, we expect all of this physics to be really well constrained, and some of it is, but of course there are also a very large number of unknowns in this that we need observational input on, particularly, this is where us observers come in many different areas. But what I'm most interested in is these sort of block of 4 in the middle that concern the origin and growth of these black holes that we've been talking about over the last day and also tomorrow, feedback from galaxies in AGN, the reionization process, and also the buildup of heavy elements in the universe. So I want to set the stage really with the AGN and reionization side of these things with just a few kind of highlights. We know that AGN have a rather complicated and hard to figure out impact on galaxy formation, really regulated under an umbrella of different physical processes that we loosely call feedback. This acts over a huge range of scales, between parsec scales up to even megaparsec scales in the cores of clusters. You can start star formation, you can quench star formation, do all of this, really complicated stuff with AGN, and we have them properly inserted into our simulations. We know that there are very tight scaling relations between the properties of black holes in the middle of galaxies and things like the velocity dispersion. We don't really know where it comes from, and the same kind of scaling between the cosmic history of the accretion rate and the star formation history. We know this is basically in lockstep. And we know now that we're particularly finding large numbers of AGN in the very early universe, pre-reionization, and we know that they must have produced large amounts of ionizing photons that they could also have had, well, they will have had some impact on the ionization process. We're just not really sure. And then sort of focusing on reionization directly, because that's the second half of this talk, if I get to it, we know that the emergence of ultraviolet radiation from galaxies heats all the surrounding gas. It's going to be a source of negative feedback in itself. We know that as soon as the universe becomes transparent to ionizing radiation, that means you can photoevaporate gas off low mass dark matter halos when the first UVB emerges, and that suppresses the formation of galaxies at small scales, giving us a fundamental scale, low mass end of galaxy formation. And then we also have the effect of this, well, the last ionization step of the universe on the cosmic microwave background. So all of this needs to be properly understood, and most of it, what's going to come in this talk, is really updates since the Shiny Gold Space Telescope was launched in August of 2022. So this talk, you may see me often saying 2 years. It's actually now 3 years since the telescope's been up, and that's the typo that I haven't been able to catch everywhere yet. So I'm just going to give some highlights of what's happened since JWST was launched. This is the number density of galaxies as a function of redshift, and the blue was what we knew before. In the last couple of years, we've established that out to redshifts 14, 15 or so, there seems to be an overabundance of galaxies compared to what we were predicting before. It seems like galaxy formation or star formation got started earlier than we would have guessed before, and there are a large number of possible explanations for this. With the galaxies are over luminous, the IMF is changing, although we're seeing galaxies that are upscattered in so-called very young bursts of star formation. There could be additional AGN that we're not accounting for, other processes going on as well. Even by redshift 7, we know that some galaxies now have already been through one or more episodes of star formation, haven't formed stars in the last 100 million years or so. So these are quenched, and we would like to figure out exactly how we can build all these massive galaxies forming very, very early in our universe. We know, for example, we've just learned that there are very many AGN out there. Maybe 1 in 20 L-star galaxies is actually an AGN. And we need to know not only how we can form the black holes, enough black holes early enough in the universe, but also grow them so they become so massive. Mass is not encoded on here, but we'll see that, I think, on the next one. Here is the black hole mass, and we've seen this plot several times as well. We have black hole mass as a function of stellar mass for galaxies. And at various redshifts here, the red ones over here on the right are all from the local universe. And it seems like when we're identifying these black holes at redshifts beyond about 5 or so, they tend to be overmassive. So even the black holes are forming and growing quickly, probably at the expense of the stars in some way. And we would like to figure this out. And the last thing I want to bring up is the fact that we've, in the last couple of years, discovered all of these galaxies, all but a handful of them, 7 or 8 or so, that have peculiar chemical abundance patterns. And you see that here on this plot, where most galaxies are down here in the black spots, and then we have a handful of these objects that seem to be very enhanced in nitrogen, and similar effects going on also in some other elements, actually. And this is kind of hard to explain in sort of standard chemical enrichment scenarios. We need to find ways in which you can overproduce or seemingly overproduce the abundance of nitrogen compared to oxygen when you have very little time in the universe in which to actually do that. And then sort of focusing on the reionization epoch once more, there were more surprises that came through the Lyman-alpha emission line. So Lyman-alpha is a great tracer of star formation activity in galaxies, but as soon as you put the Lyman-alpha emitting galaxies into a neutral universe, then the neutral hydrogen in front of the galaxies just absorbs or should absorb all Lyman-alpha. And so for a long time, the record-holding spectroscopic confirmed Lyman-alpha emitter was this redshift 6.9 source from the year 2006. And then beyond redshift of 6 or so, we found basically no Lyman, 6.5 or so, very, very few Lyman-alpha emitting galaxies. And the field sat here for some years until this single object was published at redshift of about 7.5 in 2014. And that was really a whole redshift more than we've seen before. And the field then sort of sat around here for basically 10 years until JWST turned on. And in a few months, we suddenly had Lyman-alpha emitters at redshift of almost 11, indicating that at least some regions of the universe had to be very highly ionized, or there needs to be some big bubbles of ionized regions in our universe. And that got made even worse at the tail end of last year when we started to have Lyman-alpha emitting galaxies at redshift of 13, indicating that now you can just have Lyman-alpha wherever you want in the universe, seemingly. So that's sort of the surprises that have come up. Now, I'll talk about some updates on this now. Particularly, we'll start by talking about the luminosity function and just how many galaxies are out there beyond redshift of 10. So most of the results in this field have really come, I mean, you can find many tens of papers studying the luminosity function now for JWST at redshift beyond 7. And the majority of them really coming from 3 fields. 2 fields from the goods in the north, in the goods north and south, in a survey generally referred to as JADE, so additional data coming in from other places, and 1 field in the EGS with a survey generally known, well, JWST component of which known as SEERS, and this is the kind of sizes of the surveys that we're talking about here, overlaid on the density structure of the universe here at redshift of about 10. And this is showing you that in black regions, there's very, very few galaxies, and in these cyan regions, there's very many. And it's obvious from this plot here that if your survey lands on one of these regions up here, you're going to identify very many more galaxies. And if your survey happened to land in this region over here, in an effect that we always call cosmic variance, right? There's a field variation in the number of objects returned by survey. This is really a pain when you're building surveys with these telescopes with teeny tiny field of view like JWST. You really want to have large images to do this. And the cost is when you go to very large fields of view, like we've done up here with the Cosmos Web Survey, the cost is observational depth, and then you lose the access to high redshift galaxies in a different way, because it's hard to go as deep. So one way to get around this is through what we call pure parallel observing. So when JWST is observing with one camera, you can turn on another camera to the side and just leave that one open. And if your initial pointing is long enough, you can take a completely independent galaxy survey on many skewers, many different uncorrelated sightlines. And that's what we're showing here with the little yellow points up here. These are random locations on the sky. Of course, you're not as deep, you don't have all the great supporting data, but you do have a way of getting lots and lots of observational time on the cheap because someone is already observing on the main pointing out there. And we're doing this in a survey called Beacon, which includes sort of 600 hours of pure parallel time, giving us 80 independent sightlines. And so we're sampling random skewers of the sky, looking for dropout galaxies or photometric redshift selected galaxies. And when we build the luminosity functions from this survey, what we recover here is at redshift 7 to 10, while the beacon points are in red, and all of our our recent literature points are in the gray ones up here, basically in agreement with the luminosity functions at redshift 7 to 10. And the same thing that we find redshift 10 to 13 or so. Now these are 1 sigma error bars from the survey from existing publications, and then beacon points in orange. And we're basically in agreement here. We do also find there's a large numbers of these bright UV bright galaxies out to redshifts beyond 13 or so. It gets kind of interesting here when we look at about redshifts of 15, because all of the gray data points there, they're all sort of detections of galaxies with 1 sigma uncertainties in the gray bands. And what we're plotting here is 2 sigma upper limits. So, oops, that's wrong. So we don't actually find any of these very luminous galaxies at redshifts beyond 30, not a single one in the survey now on about 20 pointings. So it's a possible explanation for some of these, this abundance of very high redshift galaxies, if they are coming from a very small number of fields. And if you more randomly sample the universe, we don't tend to find so many of them. So that's the first sort of thing I would like to draw to your attention. Just to be aware of the fact that all of these publications, you may have 100 papers working in the field, but they're really looking at a really small number of fields on very small fields. So they'll all really be analyzing the same data. That was part 1. So I want to talk a little bit about black holes, because that's the theme of this meeting, and that's where we are. So some of these galaxies we know probably do host active galactic nuclei. And of course, to improve our simulations and all of the work that all the things we've been discussing already, we need to know where they come from. And we've discussed really these 3 different channels by which you can form them. You have to begin with a gas cloud at the top of this diagram up here, and somehow work your way down to having a supermassive black hole there. And there's 3 sort of co-leading, co-competing mechanisms by which you can do this. But we certainly know that one thing that there are out there is star clusters. So if you can form a dense cluster of stars, you can generate some kind of runaway collapse and mergers of stars as they drop into the centers, eventually giving yourself some kind of a very massive star in the center that collapses to give you sort of relatively low mass black hole seeds, but large numbers of them. This is good in terms of numbers, but sort of not very good at giving you very massive seeds. We know that at some point, some form of population 3 star has to form, right? If you begin with just a universe of hydrogen and helium with no metal, there's a population 3 population out there. What they look like, we can discuss the physics of that. Here you can certainly get some forms of black holes also. Maybe light seeds in very large numbers, maybe a smaller number, or maybe large numbers of heavy seeds like the population 3.1 star model would predict. Or you can have direct collapse of gas as it streams in towards the center of dark matter halos, almost bypassing the star formation process entirely, giving you very small numbers of very heavy seeds in the process we call direct collapse. And this plot's been on the screen at least 3 or 4 times in the last 24 hours. You also have to be able to get these black holes to reach the masses at which they're observed by the redshifts at which we see them. So here are these pre-JWST quasars from Wang 2021. They're all up here about 10 to the 8.5, 10 to the 9 solar masses by redshift of 7. These are the sort of standard curves of Eddington limited growth back here, telling us that we do have to form some seeds probably in the massive regime. Some of them we can get away with slightly lower masses, but we do also have to form sufficient numbers of them. Just skip that part here. So this is our contribution to the field here. Mary has already your talk, so I had to miss your talk already, and also Alice will talk a little bit about this, I think, and probably there'll be some more. But one of the ways we thought we would try and investigate the number densities of black holes at higher redshift is through this photometric variability campaign, relying upon the fact that Hubble has a very long history of doing very deep imaging. The first ultra deep field was actually published in 2026, so we're approaching 20 years of that field in the optical, and then was imaged in the near infrared as far back as 2009. So we've been using these data combined with another image that we took about 2 years ago now. And the whole point of this is to exploit the long history of observations. This is like 10 years in the observer frame, but if you look back to redshift 10 or so, or exactly 9, and that's just 1 year in the rest frame. And this is a lot of timescales on which we expect black holes to vary. The great thing about doing things by variability is that there is no photometric pre-selection, for example. We don't have to care about what targets we want to select to put on our spectrograph. We just re-image the field. You can test for variability at some position in every single source you could identify in the first epochs. So it's very efficient in that way, and then you also have some disadvantages that you have to correct for in the statistical sense afterwards. So we have these 3 epoch images of the Hubble UDF. Here's an example of a galaxy that we identified at the very beginning of last year. These are difference images produced by Alice at the top left here, and you see that in the early epochs, you see that this source got brighter, and that's what you're seeing in this light curve at the bottom right here. You see the object get brighter from 2008, 8 to 12. And then also, if you do the same image subtraction between our new data and the 2012 data, the object gets slightly fainter. But this is about a 2-year rise and fall on the light curve in the rest frame. It's 15 years in the observer frame, at redshift of about 7. And this is inconsistent with any kind of stellar transients that we know about. So this is probably related to AGN activity. And there's this great image on the right here, also produced by Vieri, showing many more in the field. In the original paper, we found 3 sources between redshift 6 and 7. That's in the first billion years. That's in the first billion years of the universe, right? Not the first billion years of our survey. So now I think about it, it's also the first billion years of our survey. And that large number inside a very small field of view, let's not forget that this is one pointing of the Hubble Space Telescope, which is really a small field. It's a very small cosmic volume, and that translates into a very high volume density of these black holes. And that allows us to compute this number density of supermassive black holes out at this redshift. So if you look at the lower lower bound according to Poisson statistics of our raw number counts, even that's inconsistent with the most optimistic number densities of black holes produced by direct collapse scenarios, just as the number densities of little red dots is approximately on that limit as well. Now we know that not all AGN are variable, so we can make some correction for that we calibrate ourselves, and that pushes our data point up here. And then, we're not the only ones saying this. There's also the techniques used by, for example, looking at broad emission lines to measure the black hole masses. That's what you see in black here. We're sort of in agreement with these points once we make our corrections. But these are also sort of scaled to a lower luminosity limit that we can discuss in some more detail. If we want to truly compare the red points with the variability points with those from broad emission lines, we actually have to apply another correction, which drives our point up here. This is now, very, very inconsistent with some black hole seeding scenarios. And at least, it's showing us we need to be making one object per 100 cubic megaparsecs or so. And also indicating that about 1 in 10 galaxies of this redshift are actually AGN hosts. We're getting towards a point where they're probably all AGN hosts. This goes much further. So we wanted to figure out a bit more about what we could do with these variable AGN. So the natural thing that we began to do is model their spectral energy distributions, because we're working in the Hubble UDF, where we have 13 bands of HST imaging, another 13-ish bands of JWST imaging. So really the best field on the sky for that. And also complete with tons and tons of spectroscopy from JWST, from VLT News and other instruments. And we have had to build our own SED modeling tool to do this, because we found some problems with the off-the-shelf ones. And here's this example of the Redshift 7 variable source again, that we're modeling with a pure stellar population here. And we also model with a population of stars and AGN up here. And if you look at the fit statistics, AGN is sort of somewhat preferred, slightly preferred in this case, 3 or 4 sigma preferred in this case. And you see the AGN really takes over the full SED and basically all wavelengths, giving you just a little population of stars down here that are preferred in the blue. This is just one example. We have many of these, and Alice is going to give a whole talk about it. But this is really the very cool plot that comes out from this kind of analysis. I'm sorry, I really have to show it because it's really nice. These are the same diagram we saw before, with black hole mass on the y-axis and stellar mass on x. And the same low mass galaxy, low redshift galaxies over here underneath. The points that we were using to argue previously from Maialino's paper that black holes were overmassive at redshifts of 5 to 6 are the underlying white points. And our points now that we can decompose the SEDs of the AGN activity from that stellar population, or the color-coded ones, and they're color-coded by redshifts. And they indicate that at the very highest redshifts, black holes are formed at the expense of stars, which is exactly what this point plot is saying. The fact that the AGN activity is taking over. These galaxies have very low stellar mass, but very high black hole masses, admittedly with some substantial error bars at redshifts beyond 5 or so. But you do see this trend emerging when you look at the color coding, that the galaxies sort of join the local relationship of black hole to stellar mass as you evolve downwards in redshift. That was the AGN part, or part of the AGN part. And now talk a little bit about chemical abundances. So one of the, I don't know, I'm loath to use the word surprised, but because we did know about this phenomenon from the low redshift universe, I think what became very interesting with JWST is that we started finding quite a lot of these objects. If you look, JWST really gave us access to all of this amazing rest frame ultraviolet spectroscopy. And you see lines that we knew a lot about before, like carbon-3 and carbon-4 and helium-2. They're showing up in large numbers in the spectra of high redshift galaxies. What was more interesting, I would say, is the emergence of this nitrogen-3 quintuplet at 1750 angstroms and nitrogen-4 doublet at 1486 angstroms in the UV. These are probes of very dense gas, very highly ionized, very hot, very dense gas. And if you measure the strength of those and compare them with oxygen, you can use them as diagnostic of how much nitrogen is being produced, or at least if you know all the conditions in the ISM, like temperatures and densities, you can look up. We know what the collisional rate coefficients are, and they translate into densities. You can pick out that you can measure that they translate into abundances. It allows you to estimate the nitrogen-oxygen ratio, for example, up here. And that's what's shown on this diagram here. In the first, we knew about three of these sources at redshifts below 2 or 3. JWST within 2 years gave us about 7 at redshifts beyond 5 or 6. We honestly don't really know, certainly in the beginning, unclear on what these objects were. It really reminded me of the very early days of gamma ray bursts, when people used to say that there were as many theories as there were events. It was in the beginning this kind of game. AGN activity can explain this nitrogen enhancement. You can have extremely massive stars, sort of gas, the retention of gas produced in Wolf-Rayet stars in very dense star clusters. Possible tidal disruption events have been invoked to explain this enhancement, as well as very carefully balanced star formation histories. Or some combination is likely to be the case. Now, if you look at diagrams like this, each one of these is an individual galaxy. And the way these sort of studies proceed is really by trawling through the archives of 1,000 spectra, identifying the ones you think are interesting, working on those and publishing the results. And that approach is great, it's fine. It tells you what's going on in these galaxies, but doesn't tell you what's going on in the average galaxy. And that's one of the things we wanted to address about this time last year by looking at how this archive of thousands of spectra produced by JWST. And of course, you can't do it target by target, and the data tend to be rather noisy, so even the individual limits aren't that informative. But what you can do is stack large numbers of spectra together to see what the spectrum of the average galaxy looks like. And that's what's on the screen here. This is the ultraviolet portion of the spectrum. And this is about 500 galaxies between redshifts 4 and 10. And here you're seeing these UV emission lines that I was talking about. Again, carbon 3 and carbon 4, nothing unknown there. We've about those at high redshift for some years. But there's tons of other interesting things in this spectrum. And here is the nitrogen 3 1750 line. Here is the nitrogen 4 1486 line. And there's many other interesting things here. I have some boxes showing you what I just said. There's also a very strong magnesium 2 doublet here. It's also been used as a diagnostic of AGN, also very high star-forming galaxies. These tend to show magnesium 2 escape fractions of 1, which makes me always a bit suspicious. And there's this very unusual strong carbon 2 line over here. This is the quintuplet 2326 angstroms, also proposed as an AGN diagnostic. And this is the median combination of all of these spectra, which is telling us really what the average galaxy is like. Not the average flux that we're talking about, it's the average emission line spectrum of a galaxy. And then I can combine these as a function of various properties. So this is them now stacked by the oxygen 3 equivalent width. And if we can just think of that as as a proxy for the specific star formation rate, or how much star formation rate is going on. A stellar mass, or alternatively, really the age of the star formation, the youth of the star formation episode. So as you move upwards on this diagram, this is equivalent to starbursts getting younger and younger. And as that happens, you also see these lines start to emerge. What's important here is that there's a number of diagnostics of AGN and star formation and shocks, just that you can derive just by comparing the ratios of some of these lines in the ultraviolet, and that's what's shown here. These are 2 line ratios of carbon 3 helium 2 and oxygen 3 helium 2, compared with predictions from photoionization models. And you have stars up in blue and AGN down in red, and our stacks in various colors here, corresponding colors to the diagram on the left, the spectra on the left. And it seems, according to the line ratios, that they line up roughly on the star forming sequences of these plots. But what I think is really interesting is when you start to look towards the AGN to use equivalent widths on this diagnostic, because this is really telling you about how much ionizing radiation you have per unit in the continuum. And with stars, it's really, really hard to get above certain limits there, because the ionizing spectrum is really falling off as an exponential function. It almost doesn't matter what's due to the temperature. when you have a big exponential and an ionization potential above sort of 4 Rydbergs or so. And as you move through the stacks, going to the highest, what's ostensibly is the star formation intensity, you do start to push some of these points really into the AGN regions of the diagrams on average. So, and I don't want to make the claim that these are all AGN. I think that's not going to be the case. But I do think that what it's really interesting here that it could be that there's enough AGN in these samples to actually bias the averages towards the AGN point of the diagrams. Although it's true that you can get up here with some very exotic stars as well. I think that if we look at these nitrogen abundances that I talked about before, now again there's large error bars on this diagram, but if you just take the average values here, they're all shifting in the same direction. They're not pushing up there as high as these individual nitrogen 3 and nitrogen 4 detections, and that's almost by definition, right? If the lines were as strong as they were in the individual detections, you wouldn't have needed to stack the spectra in the first place to identify them. When we take the average spectra, we're finding nitrogen 3 and nitrogen 4 fluxes that are also consistent with some of this nitrogen enhancement. And this is in the average galaxy once more. So could this be the result of AGN activity? Well, it's a bit, it's not comfortable to make statements like every single one of these galaxies hosts an AGN, but yet the data would be consistent with that kind of activity. You can make the same statements about extremely massive stars and the formation of this very dense star clusters. I think that's quite likely because these stacks are based upon the oxygen 3 equivalent width, which is a sign of extremely young star formation, probably in star formation episodes, probably in very young, very dense environments, which is exactly the situation where you would form very massive young star clusters. Of course, that's also one of the formation channels for forming AGN. That is where we would expect for forming the black hole, them also to form in such environments. I find it difficult to envision that every one of the average galaxy hosts tidal disruption events, and honestly, we're also balancing star formation history. It's very unlikely that you would find the average galaxy to have a very, very particular star formation history when you average together many thousands of them. So that's where I wanted to get to with the galaxy side of this talk, and that's about half an hour. I have a whole bunch of slides about reionization, which I can skip over, and I'll leave up the sort of main takeaway points here just to get the last one, because that's where the reionization part comes in. I'm happy to talk about that as well, because I do like Lyman-alpha a lot. That's what I make most of my career do.
Great, thank you very much, Matt. We have plenty of time for questions and discussion, so we can come to the reionization as well. And but let's see then. Are there particular questions now that are urgent? Otherwise, we can go. Gino,
it's not urgent.
But no, but when I say it is urgent because you raise your hand. So
the one hand in the air is
the first one I saw.
So a few words. Can you tell us a little bit about his systematic uncertainties on getting the masses?
I could, but I'm not the main expert in the room. That says the systematic uncertainties on the black hole masses, they are substantial, right? I think a factor of 3 is considered very good. Maybe factors of 5 or 10 are even considered good. You have to ask us. So they all come from single epoch calibrations, and they're calibrated usually by using a technique called reverberation mapping. It's monitoring low redshift AGN for a long time, seeing on timescales on which the AGN, the accretion disk is basically varying, seeing the response time of the gas, backing out a size from that. You can then use dynamics to figure out what kind of mass must lie in the center. And then you correlate that with other observables like the width of the broad lines or the luminosity of a certain wavelength. So the scatter on these relationships is quite substantial, and also there could be further, I don't know, redshift evolutionary effects that come in as well. I think all this is extremely hard to pin down without doing things like pushing techniques like reverberation mapping to very high redshift. It's probably quite an ambitious project. So yeah, I think that I don't know. I don't know the magnitude of the systematic uncertainties. I'm going to say somewhere at a factor of 5.
It could well be the systematics are larger, right? Especially high redshift.
Yeah, and then there's other things too. I mean,
Yeah.
what I think is interesting is that when we compare our results by estimating the black holes by this sort of photometric decomposition of the SEDs through SED modeling, if we're just basing it off of luminosity, and when we look at the same diagrams where the black hole mass has been estimated from the width of the broadline regions, we're occupying the same regions of the diameter space. I think that's a nice and cool result. Where did it go? No, I guess I went too far. This one here, right? The white ones are from broadline region measurements underneath. The colored on top are our points, and we're not shifting things. Now, the underlying calibration data sets are probably the same, but then we are on so systematics on the reverberation mapping itself, or the black hole mass itself will still be there.
Are any of the same sources?
I would love to say that, but I mean, these are our variable sources, right? And if we had broadline detections of our sources, we would know about it.
So nobody, well, anyway, we should eventually.
No,
That's the next proposal.
Odds are 11 to 1. Yeah.
Richard has a question, so please go ahead, Richard.
Yeah, well, my question is something else, but let me just say I like this slide that's up very much. It's a nice, refreshing new idea. So that, because I worry about the systematics on even whether the regions around the black hole are in virial equilibrium at these early times. But my question relates to the nitrogen excess, and you went through various explanations, and the start. I'm surprised you didn't connect with the glob. This result has been, or a separate result related, has been discussed in the globular cluster literature for quite some time, which would really argue for this, star cluster hypothesis. But what I find, and I'm not an expert on this, but when I go and read those globular cluster papers, there's never been a resolution of what causes it. Even in, forget high redshift galaxies, just go and measure the abundances of stars in the globular clusters. And this nitrogen excess has been seen relative to oxygen, discussed in the context of the CNO cycle, but there's never been a clear-cut explanation of what's going on. And so I think it's still a mystery. And I wondered whether you'd read that literature and, because it's related.
Yeah, parts of it, yes. But my approach to this has been more to talk to people that work in the field in my department. But yes, I know that globular cluster people aren't happy with these results either, right? There's a...
But for everyone else's benefit, the globulars have similar enhancements at similar levels. Is that the main point?
At the same levels, that's actually a good question.
That I don't know. It's been, what you would expect from CNO cycle evolution doesn't match the abundances that are seen in some of the globular cluster stars. Yeah.
Yorick, is your comment directly related?
Oh, right.
Yeah. Yeah, that's exactly this. So, I mean, the globular cluster community have come up with a number of suggestions over the years, such as AGB stars and rotating massive stars, and I believe neither of them. And now the AGB stars will find it very hard because it takes about 1 billion years to make AGB stars. So it's quite, if these things are related, then it must be very massive stars, I think. And, so I wrote a paper in 2018 about the globular cluster question, suggesting these very massive stars, and more recently for the nitrogen announcement as well. And I think when we do our yield calculations in Higgins et al. 23 and 25, we find sodium-oxygen anticorrelations, which are similar to the nitrogen-carbon anticorrelations in globular clusters, which can explain this. So I think there is a solution. It's just that not everyone has accepted it yet.
Already, yeah. How much? I think I asked this at the Oxford conference. When you see excess nitrogen, is a single supernova enrichment enough to?
No, this is winds. This is nothing to do.
It's all winds. Well, okay. Is a single massive, very massive star needed, or do you need hundreds of very massive stars?
you need quite a few. It depends on what you're trying to explain. So, like in R136, 7 very massive stars can explain the helium-2 emission and the nitrogen abundance in the young globular cluster that we see. So these very massive stars are not just coming out of a computer. We see these stars, right? And we understand these stars, at least reasonably well. And to do the same then at higher redshift, like in cosmic noon, for the sunburst arc, we can play the same game and we come up with the right kind of numbers. So in the winds from these very massive stars, you can make 1 solar mass of nitrogen. And if you then extend that to GNZ11, yeah, you have a bit higher numbers, a couple of hundred solar masses or so. So you need a couple of hundred of them. But the numbers add up. Now, we haven't done the full population synthesis of everything yet, but back on the envelope can explain it.
Yeah. So let me ask Matt then. I was going to ask this question about your stacked spectra here. Have you looked at the dispersion around the stack in the sample as a function of wavelength?
That's exactly what the grey band is on this plot, if you look very carefully.
Well, okay.
So it's there. That line there is the, so these are, I don't know if it's in this plot. It is in this plot. It is in this plot, yes. So the blue plot, the blue line that you see is the median of the spectrum, and the grey regions that you see surrounding it are the 16th and 84th percentiles of the sample that went into it. No, is that true? It's run through a bootstrap analysis, and it's the percentiles of that.
So do certain lines show more dispersion, and perhaps even more than that, like the high-end detail, the high-end, so we might have to go beyond the 84%.
To separate out signal to noise from that as well, but yeah. The lower bound here, there are 1750 almost consistent with not
because
very
if
many signals.
something comes from very massive stars, presumably that would have higher dispersion.
It should have higher dispersion. Yeah, I mean, that's true. The other emission lines are also a result of, there being different numbers of very massive stars around, particularly the helium-2. What would be the most stable line? You want to compare something. I mean, if Lyman-alpha were really reliable, that would be very good. If you want to normalize that by something that's really tracing number of sort of average number of visits.
Well, maybe we can think of that during our little workshop here.
Maybe, I guess carbon 3 might be the next most stable line, which is the strong one there, which is good.
Okay. Anything else on the remind me the AGN scenario here. How did the AGN get high nitrogen? Is it an excitation?
Yeah, that in part, yes. I mean, the ionization potential of these lines is high to the nitrogen 4 is 43 electron volts. Is it up there somewhere? They're not extremely high.
So it's by changing the hardness of the radiation field, is it?
Yeah, I mean, you see it on the diagnostic diagram.
Then somebody might not have.
Here I change this is oxygen 3 versus helium 2. So as you push, this is helium 2 in both cases. So your AGN lie low down here because of this is ionization.
But is that then because the observer has not accounted for that they've inferred?
Sorry?
So the reason then the point is high is because the observer has not accounted for the correct radiation field and then put the point high, and really you're saying it's not that high.
I'm not sure, to be honest.
Maybe Devesh. I know Devesh is once, and it could be about the nitrogen. Is it Devesh?
Yeah, you guessed it, Jonathan. Yes. Thanks for the great talk, Matthew. I was just wondering, yeah, exactly. Professor Wink wonderfully said about the very massive stars being a great candidate. I'm just wondering if we can push the mass limit just slightly up to 1,000 solar masses or so. I know you work with Annalisa Citro, and she's showing that now she can use like these galactic chemical evolution models, and it's mainly these very massive, extremely massive stars that are actually showing you do reach this correct nitrogen abundances, and if you take any other combination of populations, you don't get to these high nitrogen abundances if you use these galactic chemical evolution models. So I was wondering, like, what your thoughts are on stars being slightly more massive, extremely massive stars, as you mentioned.
My thoughts on allowing there to be slightly more massive stars. Oh, I'm completely agnostic. You can make stars massive if you like.
Well, the dispersion would go up then. So you have fewer of them, presumably. So again, that's something we might want to look into.
How you populate that end of the IMF. I mean, then of course, yeah.
If I may, the question, Jonathan, you asked Professor Wink about how many very massive stars you need. I think for supermassive stars, we would need even less number of those, which is good, right? We're just following this IMF. So instead, one or two of these stars would do the job. If you have 1,000 solar mass star, you'd produce about 40, 50 solar masses of nitrogen
Hmm.
coming from these stars.
Right. Well, then again, there's this, we can look for the signal in the dispersion. I want to go to the other topics that Matt raised and also the topic he didn't raise. So perhaps we can start with reionization. Give us the 5 minute, up to 5 minute summary of the main points you want.
5 minute up summary of reionization.
Well,
all right.
yeah.
Okay. These, the most recent plot. These are, okay, so using I'll have to go back and explain the method. So Lyman-alpha is produced by star-forming galaxies, and it has this sort of typical intrinsic shape, profile shape that you see by the gray plots, the gray spectra on this line. These are in velocity space. The red peak is shifted, typical double peak profiles with the red peak shifted because of radiative transfer effects. If you were to put these galaxies in a neutral universe, you would basically eat off all of the flux bluewoods of the Lyman-alpha emission line, and you would kill off that side of it. If you put it in a very dense, high column density neutral universe, the damping wing from that Lyman-alpha would also, from the damping wing from the hydrogen absorption, would also kill the red wing. And this we've been seeing in large numbers of spectra for some years. Now, if you put that galaxy instead inside an ionized bubble, then the universe has to, by the time radiation transfers from the galaxy to the edge of the ionized bubble, the universe has expanded a little bit, and that redshift of sort of 2 or 3 angstroms of the Lyman-alpha emission line compared to the damping wing velocity allows some of the Lyman-alpha then to be emitted. So we built a model to explain, to estimate, and the point, and the influence of that is the effect on the Lyman-alpha emission will depend on how big the ionized bubble is, and because the wing of the damping wing isn't a flat step function, it also shifts the Lyman-alpha emission centroid slightly to the red. So we built a model that accounts for the distribution of intrinsic Lyman-alpha equivalent widths, their velocity offsets, and how you would observe those inside of ionized bubbles of various sizes. And here are some of the results that we found, for a sample of about 35, is it? I can't remember now. It's 25 galaxies with JWST spectra. And these are the inferred bubble radii that we estimate as a function of the redshift of the galaxy. You see that this does seem to increase slightly and slowly move towards lower redshifts, which is consistent, of course, with a picture where small bubble, the first galaxies to turn on in the universe, particularly rather small bubbles, and the bubbles grow and grow as reionization proceeds, and ultimately by the end, redshift 7, 6.5, most of the bubbles start to overlap. This gray band that you see on the plot here comes from a cosmological radiative transfer simulation from Geary and Mellimer just a year before we wrote this paper. This is sort of spanning the same kind of sizes out here. Oh no, this is a sample base.
So what range of sizes are you sensitive to?
Well, that's it. So you have to have a bubble that's big enough to give you Lyman-alpha that's bright enough to detect. So there's probably a lower limit there. Also depends on how luminous the galaxy is in the middle of it, and also how many, because we don't really believe that one galaxy corresponds with one ionized bubble, right? We know galaxies. The best place to find a galaxy is next to another galaxy, and most of these bubbles are probably ionized by galaxies working together. And then you lose sort of this upper bound here is probably not real. This is probably where we just lose the damping wing part of the profile is just so flat. So it's basically probably the limits that our sensitivity range is really what's on this diagram. Probably a smallish fraction, a quarter of a megaparsec to about ish.
So you'd worry if those limits change the redshift, you'd have to worry about that.
Sorry?
If those things you're sensitive to are changing with redshift, then you might want to
those things should probably not change with redshift. That's just a matter. All that matters is the velocity offset of between we think of it as velocity offset between the ionized medium and the galaxy itself. Now, of course, if the intrinsic properties of galaxies start to change, then we have a problem.
Well,
Because we have to build the input model at lower redshifts where you can.
In some sense, that's what you're going after now. Okay,
that was part of it.
That's part of it. Okay, one more minute on this, maybe.
Sorry,
maybe a couple of minutes on this.
This is another pure parallel program. Same philosophy as the beacon survey I talked about describing the luminosity function at the beginning of this talk. Instead of pure parallel imaging data, this is pure parallel slitless spectroscopic data taken with NIRISS instrument. So what we're doing here is taking blind spectroscopy of the entire sky with no slits or anything like that to disperse everything in the field with a low resolution spectrograph on NIRISS. Here we had about 400 hours of blind slitless spectroscopy in the J band with JWST. So this will give you Lyman-alpha emission at about redshifts of 7.5 to 9.5 or something like this. And here are some of the predicted data that predict the simulations that we ran when we wrote the proposal in the beginning. The data are going to look like this kind of mess, right? Some sky and then some blippy emission lines. Because you have two direction dispersion on JWST, you can identify these emission lines and triangulate them and find out the position of the galaxy. This is the principle that we're using in another line for the spectroscopy program. We NearSpec, and we try and develop that technique. But these are simulations. And the real data looked like this. So we looked at the 4 fields with NIRISS, and we actually found 4 of these emission lines. That we think are Lyman-alpha at redshift sort of 7.5 and upwards. These are 2 direct images, and then we find this is on Lyman-alpha emission line or a Lyman-alpha emission line in the dispersed data. All of these fields have either very deep HST or JWST and Subaru imaging. So we know that these are not, we suspect that they're not low redshift galaxies. There are no other emission lines in the spectra that there would be if this were O2, O3, or H-alpha. So we think these are consistent with being Lyman-alpha emitters. It's a larger number than we would have expected from 4 fields, which is kind of interesting because now we could do our best to derive luminosity functions with 4 galaxies. Which I understand raises some eyebrows, but if you just think back a little bit, we will find luminosity functions being constructed with 1 galaxy, and it wasn't us. And these are the luminosity functions that we derive here in the green line based upon the assumption that all sources in this survey are real, with an average redshift of about 8. And we're comparing these in this figure with reionization simulations. I think they were done by Anne Hutter. That's what the H23 is, at various different redshifts. And our the numbers that we're finding here are kind of consistent with the expectations about redshift 9 or so.
Great. So what's is there anything that's requiring some not non-normal galaxy, or you need this business with AGN or galaxies? Perhaps you can comment on.
Well, from this is completely, this doesn't care what ionized the universe. I don't know. I don't think, to me, there's no evidence that we really need AGN to reionize the universe. Now, I think they probably must have had a contribution. I wouldn't like to speculate myself on what.
So how would we really nail it down?
Okay, so how do you actually determine the difference? So there will be implications in the heating of the intergalactic medium. AGN, once you turn them on, problems arise with the AGN scenario at the end of reionization, where they would probably do the last part too quickly. And I think that what we're seeing with these large residual islands of atomic gas is that the sources were probably softer spectra. That's consistent with being stars. We can find you can find the galaxies and you can find the AGN, and in the observational sense, that's actually quite easy.
So maybe
Given that we can't detect ionizing radiation at all from redshifts beyond about 4, because they all those ionizing photons get stuck in the IGM. Attributing a cause becomes extremely difficult.
Well, we have to think then, maybe do a direct census then. You're saying just really characterize the host in a population.
I will talk about this in
great.
Oh, very good.
Very good.
And the answer is the Lyman-alpha forest.
So yeah, okay.
Very good. Well, we're nearing the hour here when we stop Origins colloquium, but are there any last questions for Matt?
I have a question.
Please.
So my question is more on the gravitational wave front, if that's okay.
You could ask the question.
No. But basically, most of the gravitational waves we've detected so far are from isolated sources. But there's this interesting new possibility of observing stellar mass black hole mergers around AGNs. So I wonder if you think at such high redshifts, it's possible to detect such gravitational waves.
You're asking me if it's possible to detect stellar mass black hole mergers
around AGNs.
Around AGN. I'm going to have to defer that question to someone that knows about gravitational wave detection.
Because I'm thinking that given that
it sounds like a nice idea.
Given that it's not like confirmed that these sources are AGNs, such mergers would have like unique eccentricities from which we know that they are AGN. So if we happen to detect them, then this could confirm that those are indeed AGNs.
Yeah, well, we'll have to think about that. Maybe Lisa can do something here. We'll have some talks later in the main workshop about that.
Those extreme mass ratios.
Yeah. Very good. More to ponder. Anyway, let's thank Matt again for a great talk and discussion.